Hello students, welcome to lecture 15 of your course Elements of Discrete Mathematics. In this lecture, we are going to discuss the applications of a bipartite graph, complete bipartite graph, Hall's theorem, and Konisberg's bridge problem. That was the main foundation stone of this graph theory, and the solution of this Konisberg bridge problem was given by Euler. So there are certain type of graphs which are known as the Euler's graph. So first, we already discussed in the last lecture what is a bipartite graph. Then we are discussing this topic matching. Okay, in bipartite graph, what is the significance of matching and what we are calling it as a matching. A matching M in a simple graph GVE is a subset of the set E of edges of the graph such that no two edges are incident with the same vertex for example, if you understand this meaning of this statement, you see, if we have this V1 and this is V2, suppose you have partitioned V into two sets V1 and V2. Then suppose these are the vertices in this and vertices are there in V2 also. Now if we are having an edge which is incident upon this, then this is a matching. Again you see, and therefore this is a matching here. A matching M is a simple graph. Matching in a simple graph G is subset of the set E of the edges of the graph such that no two edges are incident with the same vertex. For example, if I write here, if I put one more vertex here and let this vertex is incident upon this one, and let this vertex is incident upon this one. So how many edges are there? I can say that E1, E2, E3, E4 and E5. Now you can see that these two edges are incident upon one vertex. These two edges are incident upon this one vertex. So in fact, if we see, there is one edge which is incident upon only one vertex, that is this one, E2. E2 is the edge which is incident upon only one vertex, not on the two vertex. Otherwise, the other vertices are incident upon the two edges are incident upon the single vertex. So if I say the edge set is E1, E2, E3, E4 and E5. And if I look at the matching is the subset of E, and that must consist only those edges which are not incident, which are incident on a single vertex only, and no other edge is incident upon this. So this edge E2 comes in matching. Now the maximum matching is a matching with largest number of edges. We say that matching M in a bipartite graph G with bipartition V1 V2 is a complete matching from V1 to V2 if every vertex in V1 is endpoint of an edge in the matching, or equivalently if the number of edges in M is equal to the number of vertices in V1, then we say that such a matching is a maximum matching. Now next we are coming to one problem, that is the marriage problem here. So in marriage problem, what is the situation? Suppose we have a set of males. Suppose M1, we are keeping this as a vertex, M2, M3, M4, and M5. And the set of females, suppose we are having K1, K2, K3. Here I'm saying this is males and females, K4, K5, and even more number of females can be there or more number of males can be there. It is not necessary that equal numbers is there. Then we have to find matching here. Actually, if normally when preference orders are given, suppose first we are looking at the preference of the males, that he is giving the first preference to the female K2 and the second preference to K1 and like that, and not giving any preference to these. So suppose this is preference 1, so that is why according to preference some weights are assigned here. So based on the preference, suppose this is the preference 1, M1 is giving the preference 1 to K2 and M1 is giving the preference 2 to suppose this K3, and similarly M2 has no other preference and he is perfect with M1 and K1, and similarly M2 suppose is giving preference to this, and M3 is also giving preference to K2. So this is the preference of M3 and preference of M3 here. So like that, suppose this is the first preference, so I'm writing here 1. Suppose this is the second preference, writing here 1. Suppose this is the first preference and this is the second preference, like that. So in this way we can identify the matching here, or the perfect matching. The perfect matching is one where there is no other choice, that M1 is having no choice rather than apart from K1. So this is the perfect matching. So M3 is not a perfect matching. Here M4 and K5 is a perfect matching. M5 and K6 is a perfect matching. So that is how this problem can be considered as a problem related to the bipartite graph. This becomes the set V1 and this becomes the set V2. This becomes the set V2. Right? So regarding this, we can formally see, suppose there are M men and N women on an island. Each person has a list of members of opposite gender acceptable as spouse. We construct a bipartite graph V1, V2, where V1 is the set of man and V2 is the set of woman. There is an age between a man and woman if they find each other acceptable as spouse. A matching in this graph consists of a set of ages where each pair of endpoints of the ages is a husband and wife pair. A maximum matching is the largest possible set of the married couples. A complete matching of V1 is a set of married couples where every man is married. Complete matching means a set of married couples where every man is married, but possibly not all women. And the similar situation can occur in a job assignment problem. A job assignment problem can also be considered as a bipartite graph to assign jobs to employees so that largest number of jobs are assigned to employees. We seek maximum matching in the graph that models employees' capabilities. For example, in the marriage problem, there was the preference, and in the assignment of the job, there is the capability, which job a particular employee can perform with his best capability than the second job, which can he perform a slightly lower capability, and like that. So we can assign employees to all jobs. We seek a complete matching from the set of jobs to set of employees in a job assignment problem. Now, how we obtain the solution of such problems? For solution of such problems, one theorem was given, and that theorem was given by Hall, and that is called Hall's marriage problem. But before the statement of the Hall's marriage problem, we give one notation. We denote by NA the set of all vertices in G that are adjacent to at least one vertex in A, that are adjacent to at least one vertex in A. And we state the theorem here. The bipartite graph G equal to VE with bipartition V1 V2 has a complete matching from V1 to V2 if and only if number of elements in NA is greater than equal to number of elements in A. This two vertical line denote the number of elements. Number of elements in NA. And this denotes the number of elements in A for all subsets of A of V1. In fact, you have partitioned the set V into two sets, V1 and V2, and suppose there is one set that these are the vertices here. Let the set is A, and some vertices are beyond this A, and certain vertices are there in set V. Now just look at this. What is NA? NA is the set of all vertices in G, set of all vertices in G that are adjacent to at least one vertex in A. Means if I say I'm putting it here and putting it here like this, so here I can say there are three vertices. There are two vertices which are adjacent to at least one vertex in the whole graph G, because this is adjacent to this vertex. Now this is adjacent to two vertices. So you have to find the set of all vertices in G that are adjacent to at least one vertex in A, at least. So here in this situation I can say that number of elements in A is equal to 2, because two vertices are left which are not adjacent to any of the vertices in the whole graph. So that is why we will consider only these two which are adjacent to at least one vertex in this graph G. So this is NA, and if we look at A, the number of element in A is equal to 4. Okay, so for a complete, according to Hall's theorem, the bipartite graph G with bipartition V1 V2 has a complete matching from V1 to V2 if and only if number of element in NA is greater than equal to number of elements in A. So this is the situation. Now there is one exercise. Find all possible subgraphs of the following graph. Second, for which value of m and n, kmn becomes a regular graph. Third, if a simple graph G has vertices and mv vertices and e edges, then how many edges does G have? The third problem. So these were the numerical problems. Now we are coming to a very famous problem of the graph theory, that is the Konisberg's bridge problem. So in the picture you can see that these are two islands. And these are the first island and the second island. And these islands are situated in a river, and this river has banks. The bank 1 and the other bank of the river is here. Right, and this island is connected with two bridges from this bank and also from the two bridges from this bank of the river. Further, the second island is connected with one bridge and connected with one bridge from other bank. In addition, these two islands are also connected by a single bridge like this. So this was the situation, real situation, and it was there in the town of the Konisberg, Prussia, now is called the Kaliningrad and part of the Russian Republic, was divided into 4 sections by the branches of appraisal river. These 4 sections included the 2 regions on the banks of the appraisal river and Neef Island and the region between the 2 branches of the appraisal. In the 18th century, 7 bridges connected these regions. That figure here depicts the situation. Now what was the problem here? The town people took long walks through town on Sundays. They wondered whether it was possible to start at some location in the town and travel across all the bridges once without crossing any bridge twice and return to the starting point. That means that was the problem. People thought that if someone is starting from this location and he travel through all the regions of the city, for example, regions means the 2 banks and these 2 islands, crossing all the bridges exactly once means all these land parts should be covered and each bridge should be crossed exactly once, and then the person should return to the same location here again without crossing any bridge twice. So is it possible or not? So that was the problem thought at that time, and the solution of that problem was given by the Swiss mathematician Leonhard Euler. He solved this problem and his solution was published in 1736. In fact, he has put this problem in the form of graph. So actually the island here, you see, this island is considered as A and this as B. And this land part is considered as, according to this, C. This land part is C. The whole part, land part C, and this part is D. Now you can see this A is connected with this through the 2 bridges, and this also by the 2 bridges with D. So the situation has been written as, this is the island, this is one bridge, another bridge, and again one bridge, another bridge to the second bank. This is the bank of the river, and this is the second bank of the river. Second bank, this is the first bank. This is the island 1, and this is the island 2. Now these 2 islands also have one bridge to cross over here, and the second island is connected to the bank by one bridge here, and the second bank is also connected with one bridge. So that is how this problem was represented as a graph where A, B, C, D are the vertices of the graph, and these are the edges. 2 parallel edges here, 2 parallel edges here, and these are the single edges between these vertices. Then Euler gave some definition. If some closed walk in a graph contains all the edges of the graph, if a closed walk in a graph contains all the edges of the graph, then walk is called an Euler line, and the graph is called the Euler graph. And graph is called the Euler graph. And Euler, to give the solution of this problem, Euler proved one theorem. A given connected graph G is Euler graph if and only if all vertices of G are of even degree. So this was the Euler's theorem. Now let us see here in the Euler line. Again I repeat it here. If some closed walk in a graph contains all the edges of the graph, all edges must be there, but vertices must be because in a walk, in a closed walk, the vertex must appear exactly once. That means vertex must appear exactly once. Actually edges must appear exactly once. That means you will not cross any of the bridge twice. So if such situation occurs, then that will be an Euler line and the graph will be an Euler graph. Now the problem of the people of the city was that, is it possible that we start from one point or one vertex and after crossing through all the edges exactly once and return to the same point? In fact, the problem was equivalent to find an Euler line in this graph or this graph becomes an Euler graph. That was the situation. But for the Euler graph, Euler gave one theorem. A given connected graph G is Euler graph if and only if all vertices of G are of even degree. But now in this problem, what is that? The degree of this vertex is 1, because of this is 2 and 3. The degree is 3. Here degree is 1, 2, 3, 4, 5. This degree is 5. Here degree is 3. And again here degree is 3. So you can see in this graph there is no vertex of even degree. So therefore this is not possible in this graph that we start at a vertex, cross through all the bridges, and again return to the same point. The bridge, each bridge must be crossed exactly once. So it cannot happen in this graph because the condition of Euler is not satisfied. If the degree of each of these vertices would have been even, then it would have been possible to start from one point, crossing all the bridges exactly once, and returning to the same point. Only then it would have been possible. But now in the problem of Konisberg, it was not possible to do that. So answer of the problem is no. Answer of the problem is no. We cannot return to the same point by crossing all the bridges exactly once. These are certain examples of Euler graphs, which are not Euler graph. You can see here degrees 3, degrees 3, degrees 3, degrees 3. So this is not an Euler graph, not an Euler graph. You can see here the degree is 3, degree of this vertex, this is 2, 2, these are of even degree, but these vertices are not even degree. This is of degree 3, this is of degree 3. So this is again not an Euler graph. Not an Euler graph. Another example we see, which of the following graphs has an Euler path? So in fact you can by considering the vertices and edges you can also check that, but directly from the degrees, by calculation of the degree of the graph, you can see the degree of this vertex is 2 even, this vertex is 2 even, this vertex is 4 again even, degree 2, degree 2. So this is an Euler graph. This is not an Euler graph. How? You can see the degree is 3, degree is 3 odd, 3, 3 odd, this is 4 even. So actually in order to be an Euler graph, the degree of all the vertices must have been even. So this is not an Euler graph. Here you can see the degrees, all the degrees are of even. You can say degree is 2, here degree is 1, 2, 3. Degree is 3, in fact degree is 3, here again degree is 2, degree is 3. So actually we are talking about an Euler path. If we have an Euler graph, then definitely it will have an Euler path. But now you see, is there any Euler path which from this graph can we identify an Euler path which has the even degrees only? So we can identify, as it is given here, A to C, C to D. When you are going A to C, C to D, then D to E. In fact, again the degree is coming 3. I think the answer should be no here. Yeah. So this is about the Euler graph and Euler's line and the solution of the Konisberg problem. That's it about this lecture. Thank you.